Hi, this is Carolyn Heiss, and I am your calculus teacher. I am so excited to have you in my class this year. So we're going to begin with our very first calculus lesson, which is called Introduction to Limits. There's a little warm-up for you to do. Often it would probably be advisable when working with the video to pause and see if you can figure a problem out and then unpause to see how you did. Give yourself an opportunity to think about the problem before moving forward. So this warm-up says, a rock breaks loose from the top of a tall cliff. The table gives the number of feet fallen. So you can see in the table, the upper row has time measured in seconds at 0, 1, 2, 3, 4, and 5 seconds. And then feet fallen, how far it has fallen, is 0, 14, 60, 150, 250, 396. And the question asks, how fast was the rock falling at 3 seconds? So pause the video and see what you come up with. All right, so how fast was the rock falling at 3 seconds? So you would think of a measure of rate of change, something like miles per hour, the way you drive a car. In this case, it would be feet per seconds. And the word per in math usually means division. So the way you would solve this problem is say, okay, I want to know how fast it's falling at this specific time, 3 seconds. So I'm going to go to my table and look for the time of 3 seconds and then say, well, if it's falling in feet per second, that means I'm going to take the number of feet and divide it by the number of seconds. So that's going to be 150 feet divided by 3 seconds, which equals 50 feet per second. So a very helpful tool in calculus is often to look at what units your answer should be in and what you have in the problem and do the math with the numbers that would get you the units you're looking for. So division was the operation we needed to use here. Okay, that was just a little warm-up to get our brains turned on to mathematics. It might have been a while. And now we are going to look at problem number 1. Now, this is a lengthy problem. There are a lot of parts to problem number 1. It says the existence of a limit as x, and this arrow is red, approaches. So whenever you see that, you're going to say, oops, approaches. So as x approaches c, never depends on how the function may or may not be defined at c. So in this problem, we see 4 graphs. The first graph is a super easy graph. It's one that you probably would have learned how to make in Algebra 1, perhaps even earlier than that. Okay, so what we're looking for here is the limit as x, and there's that arrow again, approaches the number 1 from the right side of the function f of x. So what does that mean? Well, that's what I'm here to teach you. So the x value is going to 1 on the right side. So that means coming from the positive side of the graph, coming from the right side of the graph. As my pen gets closer to the x value of 1, what is the y value, f of x is like y, on the function getting close to? Well, I mean, you can just read it off of the graph. When x is 1, y is 3. Okay, so the limit as x approaches 1 from the right side of the graph of f of x is equal to 3. Right there. Now, the next one says, what is the limit as x is approaching the number 1 from the left-hand side of the graph? Well, I've got news for you. It's going to the exact same y value. it's going to 3 there on the left side. If I'm sliding along this function coming from the left side of the graph and then whoop, my x value is now 1, guess where my y is? It is at 3, just like it was coming from the right side. So since the right hand limit, which means the limit coming from the right side, and the left hand limit, the limit coming from the left side, are both the same, they're both equal to 3. That means that the limit as x approaches 1 of f of x, like overall, left and right, both sides, is equal to 3. Those have to be the same in order for this one to have an answer. We'll look more into that here in a minute. And now what is f of 1? This means like what is the coordinate pair that is defined on the graph when x is 1, y is 3? Well, that might just be the most boring problem that we do all year long because every single thing came out to 3 and it was just like reading a point on a graph. But now we're going to step it up a little bit. Look at this next one. It's very similar to the first graph. Both have a line graphed with a y-intercept at 1 and a slope of rise 2, run 1, a slope of 2. But this one has a little hole in the graph called a point of discontinuity. So something has been removed from this graph, and instead there's another point located at the coordinates 1, 1 on the graph. So let's see how this little removed point and relocated point has changed our answers, or maybe it didn't change them at all. So what is the limit as x approaches 1 coming from the right side of the graph of the function f of x? This might bring about a little question in your mind. The graph looks like it's headed to the y value of 3 when x is 1, but it doesn't actually hit 3. It actually equals 1. So which is it? Is it 3 or is it 1? Well, let me give you a little explanation of the word limit so that you will have a better understanding. A limit is a y value that the graph approaches. So it doesn't actually matter when you're looking at a limit what the y value really is. Here the y value really is 1. It's not approaching 1 though, it's approaching 3. It's getting close to 3. It's like, oh, I'm close, I'm close, I'm close, I'm really close to 3. As my x slides in towards 1 from the right hand side, the value of the function looks like it is approaching 3. So even though it's actually 1, it is approaching 3. And this is why it says the existence of a limit never depends on how the function may or may not be defined at c. C being the number that x is approaching. So as x is approaching 1, it looks like it's getting close to 3. So that is the limit. It doesn't matter that it's not actually defined to be 3. So then the next one says, what is the limit as x is approaching 1 from the left side of the graph? So sliding in from the left side. What y value is it that my graph is getting close to? What y value is it that my graph is approaching when I'm coming in toward the x value of 1 from the left side of the graph? Well, it's also approaching 3 from the left side. Now, what is the limit as x is approaching 1 of the function f of x? If these two numbers are the same, the right-hand limit and the left-hand limit are the same, then the overall limit of f of x is also equal to 3 as x is approaching 1. So far, this is looking very much like our first one, but here's where it's a little different. What is f of 1 actually defined to be? When x is 1, y is 1. So f is defined to be something different than what the limit on the left, on the right, and overall is for this graph. So the actual point that's defined is different from each of these limits. Okay, moving on. This third one looks a whole lot like the last one we worked with. We again have this line it is graphed so that the y-intercept is 1 and the slope is 2. It has a hole, a point of discontinuity located at 1, 3. However, it does not have a relocated point. So let's see how that changes things. The limit as x is approaching 1 from the right-hand side of the graph of f of x is equal to 3. This graph is headed toward the y value of 3 on the right. On the left side, the graph is headed toward the y value of 3 again when x is going toward 1 from the left side of the graph. So that means the limit as x is approaching 1 from both sides of the graph is equal to 3. But f of 1 is undefined. Undefined means not defined. There's no point there. There is a hole in the graph. There's not a relocated point. If you were to look at the domain of this function, 1 is not included in the domain. It's undefined. Now, this last one here is a little bit trickier. I would suggest that you pause the video and give it a try on your own. It's okay, make a guess. I don't expect that you're necessarily going to get it right, but maybe you will. Give it a shot. Okay, so the limit as x is approaching 1 from the right-hand side of the graph. My graph, if I'm coming in from the right toward the x value of 1, the y value my graph is approaching is 3. Did you get it right? I bet you did. Okay, now, the limit as x is approaching 1 from the left-hand side of the graph, coming in from the left side, headed toward the number 1. The y value that my graph is approaching now is -1. This is the first time the x value matched, but the y value did not, because this graph, it's like a completely disconnected pair of pieces. So the limit as x approaches 1 overall of f of x, it's not 3 and it's not -1, because it would have to be going toward that same value from both sides of the graph. Since it's not coming to the same value from both sides of the graph, this means that the limit does not exist. So DNE is the short way we write does not exist. If you've seen the movie Mean Girls, the limit does not exist. That's what this is. So undefined and does not exist are not the same thing. They're very similar, but the reason that they are different is that they describe different things. A function being defined or undefined means whether it actually has that point on the graph. A limit existing or does not exist doesn't matter whether the point exists on the graph or not. What matters is whether the left-hand limit is the same as the right-hand limit or not. So they are adjectives that describe different nouns. This describes the actual points on the graph. This describes matching left and right hand behavior or mismatching left and right hand behavior. So f of 1, the actual point on the graph that is solid at f of 1, is defined to be at 3 here. That's where your closed circle is. The open circle is where it's left out. Okay, so we went through that pretty slowly. Now on number 2, it says use the graph of the function b of x, this is our function b of x graphed here, this piecewise function, to answer the following functions. Oh darn, I think I've answered the question. Part A, is this a function? How can you tell? Well, it says use the graph of the function. No, why would we know this is a function? For every x, there is only one y. It passes a vertical line test. Anywhere you were to draw a vertical line on this function, it would only come in contact with the graph once, no more than once. So, is this a function? Yes. For every x value, there is only one, y value. Or you could say, alternatively, another way to answer how can you tell is the graph passes the vertical line test. That would also be fine. Okay, so what type of function is it? This is called a piecewise function, which is a function where you have different equations for different domains. So you've worked with those probably in both Algebra 2 and in Pre-Cal. Now, I apologize here, my lettering is off. A, B, C, D, this should be E, F, G, and H. My apologies. So now, what I would like you to do is pause your video, and I would like you to see if you can figure out what these 6 limits are by looking at the graph, and then push play on the video to see if you got them correct or not. So hopefully you've paused the video and had a chance to work these out. On part C, it says, what is the limit as x is approaching -4 on the function b of x? So as x is going to -4, what y value is my function approaching? Y is approaching 3. The answer here should be equals 3. Okay, now D, the limit as x approaches 1 of the function b of x. Well, when x is 1, y is 1, it goes to that value from both sides, so that limit is equal to 1. C, what is the limit as x approaches 5 for the function b of x? So here's my x value of 5, coming from the left, coming from the right, both ways it's going to the same point, that point having a y coordinate of 5, so the limit is equal to 5. Now, part F. The limit as x is approaching 2 from the right. So here's my 2, x value of 2, coming in from the right side of the graph. My y value that I'm sliding towards is 3. The limit as x is approaching 2 from the left side of b of x. So coming in from the left side, as my x's get closer to 2, the y's are also getting close to 2. So the y value that the graph b of x approaches coming from the left side of 2 is 2. Now, part H says, what is the limit as x is approaching 2 of b of x? Well, since my right-hand limit was 3 and my left-hand limit is 2, and those are not the same thing, that means that the overall limit does not exist, because both the left-hand limit and the right-hand limit must be the same. So now we are going to say with math language exactly what we just said by analyzing this graph together. The existence of a limit. Let f be a function. So like here's my function. And let c and l be real numbers. The limit of f of x, so I'm going to write the limit of f of x as x approaches c, is equal to L, equals L, if and only if. So you might recall the words if and only if, especially from geometry. That's a biconditional statement. We're saying it has to work forwards and backwards in order for an if and only if statement to be true. So if this limit does not exist because the left-hand limit and the right-hand limit were not the same, sorry, I pointed to the wrong ones. This is the left-hand limit, this is the right-hand limit. Then the limit of f of x as x approaches c will equal L if, and only if, both the left and right-hand limits are equal to L. So the limit as x approaches c from the right side of f of x equals L, and the limit as x approaches c from the left side of f of x also equals L. So both your right hand and left hand limits must equal L as x is going to c on the function f of x in order for the whole limit of f of x as x approaches c to equal L. Now that I have thoroughly worked your brain from doing a whole lot of math language, let's flip the paper over and work on the next problem. Okay, so number 3. Graph the function g of x equals x squared minus 4 divided by x minus 2, where x does not equal 2, and g of x equals 3 when x does equal 2 on this graph below. And then we have some questions similar to the ones that we were asked on the front. So basically this problem is just like problems 1 and 2 that we did on the front side, except for now you have to make your own graph. So what type of function is this? This is classified as a rational function. And you should be familiar with working with rational functions from Algebra 2 and from pre-calculus. But if you're not, I want to point out that I have a little half sheet of rational functions notes that talks about how to find points of discontinuity or holes, the domain, the x-intercepts, the y-intercepts, the vertical asymptotes, the horizontal asymptotes, the oblique asymptotes, a table, and a graph for rational functions. This is linked online in Google Classroom on the website. So if you need some support with that, that is available. I'm going to kind of jump in here and remind you a little bit of how we do this. The numerator here, x squared minus 4, is what we call a difference of squares. So it is factorable. It factors as x plus 2 times x minus 2. And we notice there's a common factor on the top and on the bottom here. So those kind of divide out with each other. It's like dividing something by itself equals 1. So that means that this graph looks a lot like the graph of the line y equals x plus 2, which of course we could use like y equals mx plus b, where the y-intercept is 2 and the slope is 1, to graph this line. However, when x is 2, we're not going to graph it. That happens to be where this common factor divided out, which means that's where the hole or point of discontinuity in the graph falls. So it's got a hole when x is 2, because if I were to plug the 2 in, that's what would cause me to be dividing by 0 here. But I do need to know the y-coordinate of the hole also. So if you plug in 2 to this, y equals x plus 2, 2 plus 2 is 4, so the y value of the hole is 4. So just to kind of repeat that, you find the location of the hole by figuring out what x value would cause your denominator to equal 0, and then substitute that x value into the simplified version of your rational equation. Once you've canceled out, you've divided out the x minus 2's to get the y value for the point of discontinuity. So my hole or my point of discontinuity is at 2, 4, right here, open circle. My y-intercept is at 2, my slope is at rise 1, run 1, so there's my little line, and it does go on forever, so I'm going to put arrows on the ends. There's my nice graph. But g of x is equal to 3 when x is 2. So I have a relocated point. When x is 2, y is 3. So this point is part of g of x as well. Okay, now we're ready to answer some questions. what is the limit as x is approaching 2 from the right side of the graph of g of x? What y value is my graph going toward as I slide in from the right side of my graph going toward x of 2? Well, it's going toward the hole, which has a y coordinate of 4. What is the limit as x approaches 2 from the left-hand side of the graph of g of x? If I'm coming in on the left, the y value that my function is approaching is the same y value as I was approaching on the right. It's that y value of 4 where the hole is. So what is the limit as x is approaching 2 of g of x? Since both the right hand and the left hand limits are the same, this overall limit is 4. And what is the actual value for g of 2? When x is 2, y is 3. The y value there is 3. So the point that is defined is not equal to the limit for that x value of 2. Okay, the next 3 problems, these were intended to be done with a calculator. It doesn't say that on here, but I am letting you know today problems like these will be done with a calculator. We will learn how to do them without a calculator very soon, but today they are going to be done with a calculator. So it says find the limit of f of x equals x divided by the quantity square root of x plus 1 minus 1 as x is approaching 0. So, and then in limit notation this is written, so that's what goes in that empty box there. We want to do the same kind of problem we've been doing, but instead of making a graph like we did on number 3, we're going to look at the table in the calculator. So what I want you to do is go to y equals and type in this into your calculator. If you do not have a graphing calculator for your use at home, you can go to desmos.com and go to the graphing calculator there and type it in there. And what we want to do is we want to do a table setup so that we're counting by 0.01s. So 0.01, 0.02, 0.03, 0.04. You could also do this just by substituting these numbers in for x and actually calculating the result. Negative 0.01, negative 0.02, negative 0.03, negative 0.04. The idea here is that we're going to see what y values this graph has as we get closer and closer to 0, just numerically through the table. So I'm going to write down the values that I see on my calculator. 1.9798, 1.9849, 1.9899, 1.995. At 0, it says error in my calculator. Why does it say error? If you were to plug a 0 here in the bottom, 0 plus 1 is 1, the square root of 1 is 1, 1 minus 1 is 0, and you can't divide by 0. So it's undefined there. So I'm going to put UND for undefined, which is what I would like you to put as well. And then at 0.01, it says 2.005. 0.02 is 2.01. 0.03, 2.0149. And 0.04 gives me 2.0198. So I see numbers. Think about this as money. $1.97, $1.98, $1.98 and a little bit more, $1.99, skip 201, 201, 201, 202. Okay, notice these numbers are smaller than 2. These numbers are bigger than 2. This is getting closer to 2 on this side as I scoot in from the left. This is getting closer to 2 as I scoot in from the right. So the limit as x is approaching 0 of my function f of x is equal to, looks like it's getting close to 2. This is the best estimate we can make from looking at the data in the table. Now, let's say you thought, Mrs. Heiss, I'm not so sure. I know this looks really close to 2, and I know this looks really close to 2, but how do I know it's not going to 2.001 or something like that? Well, first of all, I'm not going to give you any that are too complicated. However, I am going to give you a few that have ugly numbers they're getting close to, like something like maybe the square root of 2 or 1/3, or, you know, a decimal, like a repeating decimal, or an irrational number, a rational or an irrational number. So if you're not sure, what I would do is go back to your table and make it count by something smaller, like 0.001. And maybe then it'll be a little bit more apparent to you if you count by a smaller number, or 0.0001. The more zeros you add in front of that 1, the closer it's going to bring you to that actual value. But just make sure that you make the table start at whatever number you're trying to get toward, because otherwise you're going to have to scroll pretty far. Okay, number 5. Actually, what I would recommend that you do is try number 5 on your own. See if you can figure out what it is, and then restart the video to see if you got it right. So it says, hopefully you've had time to do that. Stop and do it on your own and restarted the video. Construct a table to find the limit of m of x equals the quantity x minus 2 divided by the quantity x squared minus x minus 2 as x is approaching 2. So I'm going to count by 0.01s starting at 2. So I'm going to have 2.01, 2.02, 2.03, 2.04, working backwards, 1.99, 1.98, 1.97, and then 1.96. So the values that I got from my table in my calculator are 0.33784, 0.3367, 0.33557, 0.33445, undefined, 0.33223, 0.33113, 0.33003, and 0.32895. Okay, so I see a lot of 0.33s. 337, 336, 335, 334. Let's see, if I were to continue that pattern, the next number would probably be 0.333, right? And then 0.332, 331, 330, 329. Yeah, it looks like it's going to 0.333. Do you know what y value as a fraction would be closest to 0.333? Let's see. The limit as x approaches 2 of m of x is equal to, if you put 0.333, I would accept that answer, but the answer that it's really getting close to is 1/3. 0.3 repeating is the fraction 1/3, so that would be probably a more accurate answer. But again, this is from a table, so it's okay. By the way, just so you know right up front, decimal answers, final answers, should be rounded to 3 decimal places unless explicitly told otherwise, which won't happen too often. Maybe in some word problems you'll be asked to round something to a whole number, like number of people or something, but by and large, your answers should be rounded to 3 decimal places if you're giving me a decimal answer. Now, they also give you a place here to draw the graph. I'm just going to make a rough sketch. It looks like it has a vertical asymptote when x is equal to -1, and it looks like it has a horizontal asymptote along the x-axis, y equals 0. So it kind of goes like this, and then up on this side, and over like that. There's my little rough sketch of the graph. Okay, again, for number 6, I would like you to do this one on your own first and then check your answer. Before you pause the video though, I want to make sure that you enter this in your calculator correctly, because a lot of students make mistakes here. When you go into your calculator and you type in cosine, it's going to open a parentheses up, and the argument of the cosine function goes in the parentheses. So what is the argument of the cosine function here? Is the argument of the cosine function x, or is the argument of the cosine function x minus 1? Or does it even matter? Well, it does matter, because if it's just x and then you close the parentheses and you have a -1, that means it's the basic parent function of your cosine shifted down 1. If you have the cosine with the parentheses around both the x and the -1 together, then that is a horizontal shift of your cosine function 1 unit to the right, which is not the same thing as 1 unit down. So, does the -1 belong in the parentheses with the x or not? That is the question. And the answer is the -1 does not belong in the parentheses with the x. Why not? Because only the first term immediately following cosine is the argument of the cosine, unless we put a parentheses here over both the x and the -1. So this means cosine of quantity x, then -1. And when you put this in your calculator, just like on the last one, you need parentheses around the top, parentheses around the bottom. Probably should have said that earlier. Parentheses around the top, parentheses around the bottom. Or you can use the function, fraction function in your calculator, alpha y equals number 1, to enter it. But your calculator needs to know what is the top of the fraction versus what is the bottom of the fraction, and the only way you can get it to do that is by either using the fraction function or including parentheses around the numerator and the denominator to separate them. Okay, so now that I've emphasized where the parentheses go, try this one on your own. Pause your video. Okay, hopefully you've had time to pause the video and you're coming back to check to see how you did. So, -0.01, -0.02, -0.03, -0.04, on the right here, 0.01, 0.02, 0.03, 0.04. By the way, do you have to use the same values that I'm using? Absolutely not. In fact, you might want to just start with 0.001 because you're going to get closer in than 0.01. And it might be easier for you to tell what value you're getting close to that way. So feel free to go smaller. I wouldn't grow bigger though, because you're going to get too far away and you won't be able to see the pattern. The idea is as we get closer and closer and closer to this number, what is the y value that we are getting close to on the function? So you want your table to have numbers that are very close to 0 on both sides. So this is like a penny, counting by a penny. But if you want to go 0.001 and count by a thousandth, that's fine. It doesn't tell you explicitly. So basically whatever you need to do to find the pattern is what you need to do. So let's see what I got. Negative, oh no, not negative, I apologize. Just 0.02, 0.015, 0.01, 0.005, undefined at 0, surprise, surprise, negative 0.005, negative 0.01, negative 0.015, and negative 0.02. You see some symmetry here. These values are the same except for opposite signs on each side. So 2 cents, 2 cents, 1 cent, 1 cent. I'm just rounding to the penny. It looks like the numbers are getting closer to 0 to me, because here I only had 1 0 and here I've added another one. I bet if I typed in 0.001 and put that in for x, I would be even closer to 0 with my y values than I am right here. So the limit as x approaches 0 of, this one they didn't, oh yeah, it's m of x, of m of x is equal to 0. Okay. Number 7, limits that fail to exist. Example 1, f of x is equal to the absolute value of x divided by x. What is the limit as x approaches 0 of the absolute value of x divided by x? All right, well, the absolute value of x divided by x, if you're on the positive side of the graph, is always going to equal 1. Like 1 divided by 1 is 1, 2 divided by 2 is 1, 3 divided by 3 is 1, 4 divided by 4 is 1, 5 divided by 5 is 1. So we got 1s for all the x values on this side. What about at 0 though? Absolute value of 0 divided by 0, guess what? You can't divide by 0, so that's a hole. It goes toward that value of 1 everywhere over here on the right side, but then when you actually try to divide by 0, you can't do that, it's undefined. What if I'm working on these negative numbers? The absolute value of negative 1 divided by negative 1. Well, the absolute value of negative 1 is positive 1. And if I divide that by a negative 1, I'm going to get negative 1. So this is negative 1. And here I have the absolute value of negative 2 divided by negative 2, which is also negative 1. These numbers are the same, except for when I do the absolute value of that negative number on top, it becomes positive, and this one is negative. So here, this is a negative 1, this is a negative 1, and this is a negative 1. But, again, the 0 divided by the 0 is undefined, so I've got a hole there. So, what is the limit as x is approaching 0 of the absolute value of x over x? It does not exist, because the right-hand limit is 1, and the left-hand limit is negative 1. So those are different, and that means the limit does not exist. Okay. Example 2. F of x is equal to 1 divided by x squared. So, what happens as x is approaching 0? Well, let's see. If I plug a 1 in, I'm going to get 1. And if I plug a negative 1, square it, I'm also going to get 1. You could put this in your calculator. You might have seen this graph before. It has a vertical asymptote when x is 0 because you can't divide by 0, and that isn't a common factor on the top and the bottom that would cause them to make a point of discontinuity. There's also a horizontal asymptote at y equals 0, and this graph goes up toward that asymptote and right toward that asymptote, and it's reflective. It is what we call an even function, reflective across the y-axis, sort of like that. So as x is approaching 0, this function is going to positive infinity. But when a graph is approaching either positive or negative infinity, that still means that the limit as x approaches 0 of f of x does not exist, because infinity is not a number, and a limit has to be a y value. It has to be a y value that the graph is going toward on both sides. Even though the graph is going to infinity on both sides, that's not actually a number. That's an abstract concept representing unbounded behavior. The graph is increasing without bound, so it is not approaching a singular number. So the limit does not exist. If you put positive infinity, that would not be considered wrong. That is describing the specific reason why the limit does not exist. But if it was a multiple choice question, I could put infinity as an answer choice, or I could put does not exist as an answer choice. Either one of those would be correct. I wouldn't put both of them on the same problem. It would be one or the other. So just know that both would be correct. Okay, the last one, example 3. F of x is equal to the sine of 1 over x. Very important that we do this in radian mode. And guess what? We are going to be in radian mode all year long, which is the default mode your calculator goes to when you clear the memory doing a 2nd plus 712 reset. So you should be fine to leave your calculator in radian mode all year long. Just be aware that if my geometry students have learned trigonometry, they're going to switch it to degree mode, so I'll try to give you a heads up when we get there. Use the table in your graphing calculator to determine what happens as x is approaching 0. So what I want you to do is put this in y equals in your calculator, go to Desmos and enter sine of the quantity 1 divided by x, close parentheses. And look at the graph, look at the table. You may need to zoom in, but look carefully. What you're going to see, you could pause it, pause the video and do this, take a little look, do some investigation on your own. When you come back, I'll talk to you about it. What's going on with this function is that there is rapid oscillation. And I'm not talking about your normal up and down of a sine curve. I'm talking about the closer that you zoom in as x goes to 0, the more oscillation you see. It becomes more and more jagged the more inside you go. So this is the third example of when the limit will fail to exist. The limit as x approaches 0 of f of x does not exist. So there are 3 ways that you can have the limit does not exist. Right-hand limit and left-hand limit not equal to each other. Unbounded behavior going toward positive infinity or negative infinity, or even if it was going to positive infinity on one side, negative infinity on the other side. Any of that infinity business does not exist. And rapid oscillation. Not talking about smooth curve oscillation, talking about this really insane thing that's going on the closer you get to 0 on this function. This is kind of a unique function in that regard. You're not going to see this third one that often, but I'm going to assure you that I'm not going to leave out any of the special cases that arise in this course. You will know about all of them. So even though this is the least common reason that limits do not exist, we don't want to leave it out. It's unique, but it is not unheard of. So these are the 3 different situations where you might find a limit that fails to exist. I hope that you have had a whole lot of fun learning about limits with me today. And I hope you have a whole lot of fun working on your assignment. If you are puzzled at all, if something is not making sense to you, if there's something that went over your head and you need a more personalized look at it, feel free to contact me. You can email me. You can come in and see me, or we can work out some kind of a Google Meet so that we can talk about it. But I am here to help you. That is my job. That is what I love to do. And so please do not hesitate to reach out for help if you need it. Have fun learning about limits, and I will talk to you again soon. Bye for now.